Hello everyone. In this video I'm going to be talking about a project that I've been working on with Russ from RDWorks Learning Lab. He came up with this project, the Dohicky, and basically it's this little device that allows you to measure the amount of power coming out of your laser tube. So if you buy a laser on eBay or something like that and it's advertised at 30 watts or 60 watts, how do you determine if that's actually the amount of power that's coming out of it? So that's why he came up with this little device. I've taken this, added some electronics to it, and created the digital Dohicky, which is a way to see in real time how much power is coming out of the laser tube, and it has this nifty little display on it, so you can actually see it displayed right there in terms of wattage, and you don't have to do any calculations. So let's see how this whole thing works. First off, I'd like to thank Russ for creating the Dohicky. It is a great tool if you own a laser cutter or engraver. Now, I'm not going to go into a lot of the theory and everything behind this. He has a really great video on that. So if you check the description down below, I have a link to his video where he goes into the background on this. I'm just going to give you kind of a brief overview of what this is. Ultimately, what he did is he took a commercial laser power meter and then created another device that essentially acts the same way. The way that you measure laser tube output power is to essentially look at the temperature rise. So if you run the laser tube for X amount of time and then put, something like this, let's say, in front of the tube, you get X amount of temperature increase over ambient temperature. So if you convert those two together, you can ultimately say, hey, if I put this in front of the tube and I get 10 degrees, Celsius rise out of it, that translates into this many watts of power. So that's really all this device does. At the end of here, we have this little puck of aluminum. We have a tube that comes out here, and inside of here, we have a thermocouple. Thermocouple is just a temperature sensor. So by using one of these little temperature probe things, this goes into here and it just reads the thermocouple. We can ultimately look at what ambient temperature is, wave this thing in front of the laser for a determined amount of time, and then look at the temperature afterwards. And then by looking at that rise in temperature, we can look at a table that Russ has created for us. Thank you, Russ. And then we can ultimately translate that temperature rise based on this device into laser power output. So the way that you do that is you take one reading before, one reading after, you do some math, you look at the table, and then boom, it gives you your output. What I've done is I've simplified this a little bit by adding a microcontroller into the mix, so you don't really have to look anything up, you don't have to do any of that silly math, and this does everything for you. It also gives you the advantage of looking at it in real time by giving you a little display of the power output in real time. So yeah, let's look at the process of how this all kind of functions, and then what I did to simplify it with a microcontroller. Here I've got this little thermometer that I bought off of Amazon. This was about $22, so relatively inexpensive. I've got a K-type thermocouple plugged in, and this is what a K-type thermocouple looks like. The K-type is basically the type of thermocouple it is. There's many different types of thermocouples, and ultimately it refers to the temperature range. K-type is going to be the most common one, so don't worry too much about that now, but that's what this is, and these are relatively inexpensive, just a few dollars for a couple of them. And then this is the Dohicky, and I have basically this thermocouple threaded through into my thermometer. So if I turn it on, we can see that the ambient temperature right now is about 22.2, and if I was to put my hand on it, it would rise a little bit. But I'm going to use this as the kind of background reading, and then I'm going to take this over to the laser, wave this in front of the tube, and then we'll see what the reading looks like after that. I just got done running the test on the laser and I get 49.7 degrees Celsius. So you remember before it was 22.3 and this is substantially warmer now. So if we do the math, that would be 49.7 minus 22.3. We get an overall temperature rise of 27.4. Now, based on the duration of how long I ran the test and the math that Russ did, we just have a 2-to-1 ratio. So I just multiply this by 2 and I get 54.8 watts. So that laser with the, I think it was set at 80%, I was getting 54.8 watts out of it. So the system is really just this easy, but I'm going to show you what I did to make it even easier and make it a little bit slicker. The first step is to find a way to read the values and the information coming out of the thermocouple into some sort of microcontroller. So this is the thermocouple once again, and this is a thermocouple amplifier breakout that I got from SparkFun Electronics. You can see it has a big K here because it is for K-type, which this is, so those play nicely together. And on the output, it just has a couple digital pins that go into your favorite microcontroller. And over here, I have an Arduino Pro Mini, which is one of my favorites. And this plugs directly into it like that. And then now we can use the Arduino to read the information coming out of the thermocouple. And then we have a OLED screen here. This is just one of these cool little inexpensive OLEDs. I think I got this off of Amazon for like under $5, which is pretty cool. And so I'm going to use this to display all the readings and kind of the interface on here. And I just have a simple little push button for resetting those values. And I'll show you how that works later. Over here, I have a LiPo battery that is used to power the whole thing. I noticed that when I had this connected up just with the FTDI into the computer, my readings were all over the place and I just wasn't getting a good stable reading. And the reason why is that the power coming out of the computer, or whatever power you're using for this whole system, it needs to be extremely stable because that's the reference that you're going to be using when you're reading and amplifying the thermocouple. So you need a really stable voltage, so going with a battery is really the best way to do this. And when I come up with some kind of final enclosure for this whole thing, I'm probably going to go with just AA batteries or something like that. I really want to make this kind of a handheld device like this, to where you can just pull it out, wave it in front of the tube, run your test, and they'll just give you a power output value. So I'm just going to use some batteries because that was the easiest way to get a nice stable voltage through the whole thing. And I have a electrolytic and a little film capacitor, or a ceramic capacitor on here, just to smooth that out even further. So let's go ahead and turn this on and see what the display looks like. And there is the display. Right now we're reading 0 watts because there is no temperature rise over here. If I go ahead and put my fingers on it, you can see it starts going up. So it's a really simple little system, and if I want to stop it, I can just hit the reset. And you might be able to see this. I have now, which is the current reading, and then I have max, which is the maximum reading, and then this just does the calculations in real time. And if at any point you want to reset it and do another test, you literally just hit the reset and it just resets the now to the max and just, completely resets those values. The code is relatively simple. The only thing that I'm doing special here is I am doing a little bit of smoothing because the values from the thermocouple do tend to jump around a lot. So I basically have, I guess, 3 values I'm tracking. I'm tracking the now, and I'm tracking the minimum, and then I'm tracking the maximum, and then I just do the calculations based on that. So it's relatively simple. It's just a slick little interface. So I'm just going to go ahead and reset this, let this even out, and then I'll show you what the test looks like on this little device. I'm over here by the laser. I have the lid in the back propped up and taped in place just so it doesn't slam down. And this gives me access to the tube in the back. And I'm going to be using the Dohicky to measure right as it comes out of the tube. And the reason I'm doing this is because you don't want to measure it once it's been focused, because it'll just etch into the end of the Dohicky, and that's bad. It'll just etch this coating right off. So we need to measure it before it gets focused, so that's before the focusing lens, and ideally before all the mirrors. So I'm just going to measure it as soon as it comes out of the end of the tube. The digital Dohicky portion of this is already set up. I've got it pretty much evened out to ambient temperature. It's holding really steady at 18 degrees Celsius and measuring 0 watts. So I'm going to turn this whole thing on, wave this in front, and we'll see what we can do for a reading at 100% power. After running that second test, it looks like my laser is outputting 56 watts, which is exactly in line with what I would expect from a 60-watt laser tube. And of course, looking at the footage again, I realized I was running it at 90%, not 100% like I thought. So 56 watts at 90% power is exactly in line with what I would expect. So it's pretty clear that I have a 60-watt laser tube, and this seems to be measuring accurately. The next step that I need to do is pretty this up a little bit, send this out to Russ, and I want him to test this against his commercial power meter and also his other Dohicky, and I want to see just kind of how the digital version of this works compared to the other ones. I can make a little bit of calibration and adjustments in software from there, but I just kind of need to get a baseline comparison. The other thing I need to do is clean up the software a little bit. There's essentially 3 different tests that you can run, and I kind of have this hardwired just to run the one. But let's say you have a 30-watt laser versus a 150-watt laser. For the 30-watt laser, you're going to run the test a lot longer because there's just not enough power to put into this puck. Whereas if you had a 150-watt laser, you wouldn't run this really long program because it would heat this up way too much. So there's essentially a scale factor that I need to program into here, whether it be like a 1-to-1, a 2-to-1, or a 4-to-1 ratio, and you would essentially boot this up and then select what type of laser you're running, whether it be like a 30-watt, a 60-watt, or 150-watt, and then it would apply the correct scaling factor in software. So that's another thing that I need to do. And the last thing, once I get everything calibrated and know that it's working accurately, I want to pretty this up and put it in a nice little handheld enclosure so that you can just, put in some batteries, turn it on, plug in the actual probe, set the calibration setting, hit, reset or start or whatever it ends up being, and then take the measurement like that. Just, make it kind of a pretty little handheld device. Why not? So yeah, look forward to that in upcoming videos. And if you haven't seen Russ's channel, definitely check it out. If you have a laser, check the description below for his channel, and I'll see you again next time with even more videos. Thanks for watching.